Hello everybody and welcome to the third video of our classification, specifically logistic regression part of our machine learning course. And last time we learned about our hypothesis function that we're gonna use, specifically the sigmoid function, its properties. And we said that in the next video, that means this video, we're gonna learn about how we actually learn the parameters. Is it the same as a linear regression? Not. We're gonna see. So in this video, we're gonna learn about the new cost function. You know that in order to implement the gradient descent, which is here, like the third part of our video, we need a cost function. And as you see, the cost function that we're going to use for logistic regression is not the same for linear regression. We're going to do some interpretation for the function so we can understand exactly what's different, how it works. And finally, of course, after seeing the gradient descent, how it becomes, or how if it stays the same. Finally, we're gonna see logistic regression versus linear regression. We're gonna see like some comparison differences, what's equal, what's not equal, and so on. So let's start. So the cost function for linear regression is simply 1 divided by m multiplied by the sum from 1 to m, the mean square error. That's like simply the mean square error. And you can see that this cost function gives us this graph, which is convex. And if you remember, actually this is just a 2D graph, but I already in previous videos I showed you the 3D implementation of the graph. So if you remember, it's like totally convex, and that's linear regression. So it's pretty much easy like to learn. But the problem, if we like give the same cost function for a logistic regression problem, the cost function graph gonna be exactly like this. So it's gonna be like really hard to go to the global minimum. You remember the word global minimum? Like we learned that word in previous videos. So it's gonna be just like here in local minima. For example, if we start here like local minima, and there it is, like we cannot even go more and go down. So it's gonna like stick here or here, like here it's more like dangerous to stick. So it's really hard to converge to the global minima if we use the same cost function we used for linear regression. So yeah, the problem is we will stop in a very high local minimum. So we need different cost function, and that's what we're gonna learn. So yeah, logistic regression cost function. So note, we know that always y equals 0 or y equals 1. So this is the cost function we're gonna use. Don't get shocked. I'm gonna explain. First, this cost function didn't come like just like that from the air. It's actually very long mathematical work to get here. But we are not going to see all that work because, well, you can do everything without knowing that. So, and our goal is to practice machine learning, not to learn every single detail about it. Yeah, and that's what's different in our course than other courses. So -1 divided by m for all like from 1 to m, that's for like multiple features of every y multiplied by the log of h of x. X is the every single feature from 1 to m, plus 1 minus y multiplied by the log of 1 minus h of x close. So let's see interpretation to understand all of that. Don't get scared. It's gonna be all obvious and like it's just a secret between us. You won't need to know that later. So let's see some interpretation. So let's see if y, we know that y equals 0 or 1. So if y equals 1, for simplicity, let's assume that we have only one feature, x. In this case, j of w gonna equal minus log h of x. Let's see how we got from there to here. So we said assume that y equals 1. So this is 1. Okay, and we assume that m equals 1 also. So yeah, just for simplicity's sake. So when y equals 1 minus 1, that's 0. So 0 multiplied, all this get deleted. So y also equals 1. So, and this is 1, m is 1. So 1 over 1 is 1. So it gets deleted here. So we have only log h of x. And this minus. So minus log h of x. Are we right? We are right. So minus log h of x, that's our if y equals 1. We know from previous videos that h of x is always between 0 and 1. So if you have like the cost function, this is, I know you might like think, oh, this is supposed to be w, but it's the same like h of x, because you see here, like, yeah, because now our cost function is equal exactly minus log of h of x, and you can consider h of x as like a big X. So it gives us that shape. So if we want to interpret this, if h of x approach 0, the costs go so high. So if h of x goes to 0, the cost is so high. So we are wrong, because you know the goal of the goal of machine learning, yeah, and the cost function is to minimize the cost function, as we said before. So like the as much as like low the cost function goes, that means that's the right answer. So if our h of x equals like goes to 0, that means we are wrong. That means h of x it goes to 1 actually. So we have a low chance that y equals 0. That means like h of x must go to 1. So that's the interpretation. That's like this function here is like really smart, because it's like concluding all of this. Let's see the second part. And the second part is when y equals 0. As before, we're gonna assume that we have only one feature, and m equals 1. So if you replace y by 0, we're gonna have this right here, like this cost function I leave minus log of 1 minus h of x, and it gives us exactly that shape. So here the opposite. If h of x approach 1, the cost goes so high, that means there is a low chance that y equals 1. Here, if h of x approaches 0, that means there is a low chance that our tumor, for example, not our, I hope we are always like away from tumors. So the example we learned about, that means there is a low chance that it's equals 1, it's equals 0, that means it's equal 1, that means it's yes, it's benign, it's malignant tumor, and here it's benign tumor. So what about gradient descent? We learned here about the cost function, and we saw some interpretation. This is the cost function. We didn't come up with this, but believe me, like there is very hardcore math behind that. So how do we use that? We use it in gradient descent, as we learned in linear regression. So how is gradient descent gonna be? So this is the gradient descent we learned for linear regression, and it's the gradient descent, like the general form. The only thing that is supposed to be different is the derivate of the cost function, because we have totally different cost function, right? So as anyone can assume, is totally different cost function means totally different derivate of that cost function. But now this is the cost function we have, but we have a surprise for you. We're gonna have exactly the same gradient descent phrase as the linear regression gradient descent. That means the same derivates, like the derivative of this right here is the same as the derivative of the cost function of mean square error that we use in linear regression. Why? I'm gonna say by chance. It's just like total luck. It's total luck that the same derivative of the cost function for linear regression is the derivative of the cost function, this like cost function for logistic regression, just cosmetically. So that's actually good for us, because we, like, you're not going to worry about calculating complicated derivative of like this complicated thing. But if you do, you're gonna have this result, and you're gonna make sure that yes, it's actually the same, exactly the same. But there is one thing you shouldn't forget about, is that the h of x here is different from linear regression. In linear regression, h of x was equal to wx plus b, and here the h of x is actually the sigmoid of wx plus b. And here it is, like the sigmoid of wx plus b. So let's do some comparison between linear regression and logistic regression. So logistic regression is for problems with two classes, to classify things just with two classes, while linear regression is for continuous values, to do regression. The hypothesis function for logistic regression is the sigmoid of wx plus b, so h of x equals the sigmoid of wx plus b, while the hypothesis function for linear regression is the wx plus b simply. The cost function for logistic regression is all this phrase that we didn't learn how we get here, but we know it's the right one because you trust me. Thank you. And the cost function for linear regression is simply the mean square error. And we learned that the gradient descent is actually common between both of them. It's just like luck. It's luck. It's like nothing to do with math or something like that. It's just after derivating this and derivating this, it gives like the same derivative. These two cost functions give the same derivative, so we're gonna have the same gradient descent is applicable for both of them. So yeah, now after this video, we're gonna do some practice in both R and Python. And after that practice, we will see how to deal with problems with multiple classes. Until now, we dealt only with problems like the solution we gave, which is logistic regression, is applicable only in problems where we have two classes, like y equals 0 or 1, black or white, something or something else. But after that, we're gonna see how to classify between like 3 or more classes, and that's gonna be like another chapter, our 5th and last chapter of our machine learning course. So stay tuned for that chapter, and thank you very much. See you in next video, which is gonna be a practical video.